Ladies and gentlemen, we are now ready to start the first afternoon session, and we have three distinguished speakers and very interesting papers and presentations. So before I invite the first speaker, I just had I was asked to make an announcement that during the next coffee break, people can pick up their certificates of attendance and also any invoices during the break. Now, our first speaker is Professor Forreston from University of Bremen, and his title of his presentation is Advances in Microforming. And I leave the floor to Professor Forreston.
Thank you, Chairman, for the kind introduction. Ladies and gentlemen, good afternoon. I have the pleasure to proceed with the micro part of this international conference on microforming just after the lunch break. And I like to show you something what we are doing within a collaborative research center, which can compare a little bit to that center which is now from principle, which is now here implemented in Ankara. It's a collaborative research center where we have some 19 projects all in all on the topic of microforming, and I like to focus on those projects which we are running at the BIAS, so Bremer Institute. This is an institute for applied beam technologies, so using laser technology for microforming. This is a typical product which drives us in our motivation. So this has a lot of micromechanical parts. This has a connector pin, for example, and for that one needs small parts. Typically with dimensions, when we talk about microforming, we talk about parts with dimensions with less than 1 millimeter in at least 2 dimensions. So thickness and width, for example, should be less than 1 millimeter, length could be a little bit higher. When we scale down those parts, we have to scale down also the processes. And here you can see what I mean with scaling down. This is a typical normal cup with 50 millimeters in diameter. Maybe for you, especially for Professor Roll, this will be already a small part. And we scale it down to 1 millimeter or even to a punch diameter of 0.75 millimeter. And this is not easily to be done, because some so-called size effects can occur which generate other behavior of the parts compared to the macro range. And I like to show you the challenges coming from these reduction in size. One is the formability, the drawing ratio. If you take this typical drawing diagram, the drawing ratio, maximum drawing ratio, and the blank holder pressure, then you can see that if you go down with the dimension from 5 millimeter to 1 millimeter in punch diameter, the maximum drawing ratio reduces from approximately 2 to 1.8, and this is due to a couple of effects, changes in friction and changes in formability. For example, for friction, we have developed a friction measurement method which uses the process force during a bending process, and a model which then calculates the coefficient of friction as a function of the local contact pressure. And the scatter is considerable, but you can see at least the friction coefficient is low at the large dimensions and becomes bigger and bigger at the small dimensions of 1.75 millimeter of punch diameter. So this gives one reason for the decreasing drawing ratio which can be achieved. Another point is that the scatter increases. So this is the normalized scatter of the drawing force, in this case for deep drawing of cups like it was shown. and as the punch diameter decreases, the scatter of the drawing force increases very much, up to a very high value. So it means that the process will not be very stable due to some additional effects. One is that the number of grains which are deformed become less and less as the parts become smaller, and so the individual properties of the individual grains play a bigger and bigger role, and so from part to part this behavior is another one, and so it is not a metal forming of a continuum, but it is a metal forming of merely individual grains, and this gives individual forces, and for a whole lot it gives a big scatter. So it's more difficult to control this process. Well, the first thing to do due to that, we have to characterize the material properties and to try to take influence on the material properties. This is shown here for steel, mild steel in the as delivered condition, and the optimized heat treated condition, and this is tested then by normal tensile tests and by a stretch test, and gives the conventional diagrams, deep drawing diagrams with minor and major strain, and we can see, of course, due to the heat treatment, it can be improved a little bit, but if you know conventional diagrams, forming limit diagrams, you know that these curves are much higher than that optimized curve. This is due to the fact that the material also becomes in a tendency of brittle, so it has a low fracture strain. Another strange thing occurs with aluminium, which is shown here from the stretch test, two-axial stretch test, that in conventional, so mechanical stretching, we have a nearly symmetric appearance of the strains which occur, while in a pneumatic stretch test, the strain is distributed in a very strange way, so there are kind of hot spots, so parts which have a very high strain. This disappear maybe during the following straining, and other hot spots appear, and so the material behavior is totally another one in this case of pneumatic stretching for the small dimensions. The measurement were made, just a short look on the system with a GOM system, so I think meanwhile we advertise these systems very often here in today, so I am convinced everyone will buy that system if he needs something. What you can make with this is measuring the strains very nicely here for an aluminium alloy, again from pure aluminium. And we can see for the slow velocities there is no significant difference between the strains which can be achieved, while by laser shock forming, a high-speed forming process, we can have much higher strains in the parts, so there is a positive effect of the high velocity, obviously. Well, one alternative to, so this is the characterization of the material, but the characterization, of course, itself does not change the material properties. So the question was, how can we get maybe material with other properties, with better properties? And so we looked for alternative ways to produce the materials. It is produced by a PVD method. Normally you apply PVD for coating of whatever with hard layers for wear production or maybe other coating applications. In this case, we also use the PVD method to get a thin layer of 20 to 50 micron approximately of an, for example, aluminium scandium alloy. which has the advantage of high strength. But we intentionally want the layer to dispatch of the substrate and then use this layer as a material for the parts. So we produce foil by this PVD method. First it worked not very well, though the thickness was very big differences between the border and the middle. By some methods it can be equalized to thickness with low deviations from the intended value. And also the brittleness was high at the beginning, so this was the temperature where it was produced, the substrate temperature. By increasing the substrate temperature, the strain can be enlarged, but is still low for this. But this can be used already for metal forming. We use, by the way, a special machine for our microforming experiments. This is a linear motor-driven press with two punches or two stroke possibilities, upper and lower part, which can be moved very quickly up to 1,800 strokes per minute with an absolute positional deviation of maximum 3 microns. And this is being used for the experiments for such deep drawing, for example. We also use the forces which we can determine from this machine to determine the effective friction coefficient, and we see some differences between the materials produced at different substrate temperatures. Of course, there is no relevant difference for different drawing ratios, but only for the two materials, for S160 and the S73. And then we can produce, showed that we can produce such cups, and we are working on having cups with higher drawing ratios, though of course we want to have a drawing ratio as high as possible, at least drawing ratio of 2. Well, I mentioned at the beginning that we focus at my institute on methods to apply laser technology in microforming, and so this is an example of this use of laser technology. It's a laser shock forming, because the laser can be used, a pulse laser can be used to produce a shock wave, and this shock wave can be used instead of the stiff tool, the stiff punch to form the part. This is in principle shown here. Here we have the sample, the blank, and this is the laser beam, the short pulse, which produces a plasma. This absorbs the remaining energy and gives a shock wave, and this shock wave then deforms the part. This can be seen here in this nice video. For bending it can be also applied. So this is the counter here for the milliseconds. It is a high-speed video, so I show it again because it's very difficult to see. It's the beginning. You will see the part standing here, then the laser beam comes from the left. You see this plasma shortly in a few pictures, and then see the acceleration of the part. So again, here we have the microseconds. And if you count the microseconds, you will see it's about 4 microseconds for the whole forming, so you can do some 1,000 of parts per minute. So it will be really a very fast technology. We can use this for deep drawing also. These are examples from deep drawing with no counterpunch. So we get, of course, this shape here, a dome shape with a counterpunch of this diameter. We have this shape, so it looks like in the cross section like this. And we can use it also for stretch drawing. So there is no flow in from the outside, and this is stretch drawn 20 micron steel. Yes, it's a high-alloy steel, stainless steel. So for that, the forces are high enough to get a deformation at least for 20 microns. This is possible due to the fact that we are in the micro range. We also can use it for producing undercuts like that, though we can use it for joining operations, which is at the end the intention of this type of forming technology. Well, another example of using lasers is technology where we substitute conventional forming technology by using laser technology. If you want to have such a material accumulation for a fastener or whatever, then normally one uses a multi-step process with an upsetting process. In the macro range we have a maximum upsetting ratio. That means the free length divided by the diameter must be less than 2.3 in each step. So by accumulating the steps we can have a bigger effective upsetting ratio. In the micro range there again occur some size effects, so that the effective upsetting ratio may be below 1.1, so one needs much more steps of upsetting in the conventional way. And we are developing such a system, such a process, where we come to a two-step process. The first upsetting of the material is done by remelting this whole length by the laser beam, and then calibration step by a mechanical tool. And I can show you a high-speed video, but this is only works with, hopefully, with this. Let's look. Okay. So again, this is high speed. You see here the laser spot and the melting of the material. And due to the surface tension, it does not pours down by gravity, but it forms a nice sphere which vibrates a little bit, but it comes to a steady state before it resolidifies, and then you can see here the solidification front, which now goes to the top, and now it's solidified. And if I would show you this video in real time, you couldn't see anything because it's approximately 100 milliseconds, so it's just two pictures, start and end, which you would see. So it's a very quick process for producing such material accumulations. We can do this also in the middle of a wire, like this one here, and then we can use this as a starting part for further forming operations. We can calculate the efficiency. I don't want to bother you in detail with this formula, but you should know this formula gives this line here, and this tells us what is the amount of energy we need for a special upset ratio, because the upset ratio is that what the designer will tell us, and so he will tell us, okay, we will need, for example, an upset ratio of 5, and then we can look up for the normalized pulse energy by this model. The limits are very far above that what is conventionally can be conventionally be made. Remember, for conventional upsetting it was 2.3, and here it is 45. So that looks like that. So a very huge accumulation, and we even can go further up to more than 250. So this is 100 times more than in conventional technology. Though in practice it seems to be no effective limit for the material accumulation by this process. Of course, you can may think now, okay, this is a cast structure, this will be brittle after resolidification. Of course, we also looked up that, and we use a rotary swaging method also after the material accumulation for the deformation, and it can be seen that it is very easy or very good to be deformed. We also made upsetting tests, and we couldn't detect any limits from the material. We had some limits from the machine because the upsetting of this area here to a flat part was made until it was that big in diameter that the force of the testing machine was not enough for further compression of the part, and no fracture was seen. This is due to the fact that the very, very fast resolidification, which also takes place in some milliseconds, gives, of course, some dendrites, but these are very fine and fine-grained, and so it has a good formability. Well, last but not least, we need tools also for this process, for the rotary swaging. And we produce the tools here. If you ask yourself what are these numbers, these are the numbers of the projects. I'm sorry for that you don't know what are behind these numbers, but the essential thing is we need those tools, and how can we produce it. We have two different ways to produce the raw parts. I like to go only to this route here. This uses a laser technology and selective laser melting, which produces a near-net shaped part, which is then finalized by grinding and by a special chemical etching method for a detail of this edge here. Because this edge, when this is used within the rotary swaging tool, this must not be sharp, but after grinding it is sharp like this dotted line, and so we need to convert it into this radius here, and for that we use a chemical etching which is laser guided. Though the trick is that we have an etchant and which does not affect the metal. The metal is passive at room temperature, but if we increase the temperature up to, let's say, 60 or 70 degrees, then the material is solved, so etched by this etchant, and we don't increase the temperature overall, but we use a laser for locally increasing the temperature, and so we can reduce material by local irradiation of the tools. And this was used to prepare the tools. One of the advantages of this laser method is the very smooth surface that we get. It is a cold process in effect on the material, because all the material which is heated is removed by the etching action of the etchant, and though the remaining material stays cold, and so it has no cracks like, for example, in nano or picosecond ablation. The surface looks like that, having cracks and having recast or burr on it, though this looks much better after this chemical method. And due to that, we use that for getting very smooth parts, and this was the result already displayed in a smaller version. You can see it fits very good to the desired shape of the radius of 125 microns. So when going to more complex shapes, for example, to the rectangular parts, you can observe also in microforming this effect of it's not really earring, but it's a question of the draw-in of the material at the long edges. The material can flow easily into into the die, while in the edges there is a real deep drawing action, and it flows not so easy, so it gets this undesired shape. In macro production you use, for example, draw beads, but this is of course not possible when producing such a cup of 2 millimeters, and here in this dimensions I think it's 500 micron or so in width here. So draw beads of course are not possible in microforming. So what we are doing, or the idea is what we want to do, and started with that, and is to influence the friction coefficient by making tailored tools for the forming, using tool material with low friction in the corners and with a high friction at the long edges, and though reaching the same effect like with draw beads. And for getting these tailored tools, we use this selective laser sintering process, which works in that way that we have a powder bed and then use a laser, and the laser locally remelts the powder, gets a full density stiff part, and by changing the powder from step to step we can produce this multi-material tool. Well, that's essentially all what I wanted to show you about microforming. I showed you one product at the beginning. I like to show you some other products at the end. So one thing what we make is of course aiming such smaller connectors, connecting pins, what we want to make, but also there are applications which we are working on of bigger parts. This is from a razor diameter of let's say 10 millimeter approximately, so this would be no microforming part in the very concerning the definition, but the local elements here meet the definition of microforming, and so the problems also occur here at those parts for microforming. So this is another application which we are looking for our microforming results. I'd like to conclude. I showed you that, or I hope that I could show you that microforming would be a very good technology for mass production in the micro range, especially as metal forming can be a very quick technology for high production, and you have to be aware that typically the products which we look for example, also these cell phones, we have also connector pins, and so in these cell phones, and from these the yearly production is 800 million of cell phones per year. So if you need one kind of pin in it, you need 800 millions of it per year. And so a technology which produces easily 1 million parts per day is very welcome to the production. The problem that occurred during the ice effects are the increased friction, the increased scatter of the properties, and the demand for dry processing. I didn't address this, but people in most cases like to have clean surfaces to be able to join some other parts to the micro parts, because very often these are electrical applications, and though you should not have lubricant, because lubricant removal is very difficult. I showed you some alternative routes. One alternative route for the sheet material generation, laser shock forming as a classical forming technology, but using an unusual generation of the forces, substitution of a process, a multipass upsetting by the remelting process, and selective laser melting as a process for tailored tools. Thank you very much for your attention.
I would like to thank Professor Wallerstein for his very stimulating presentation. Now the floor is open for questions and comments from you. If just ask a simple question about the level of strain rates you're obtaining in laser shock forming of foils. What is the estimate of the strain rates which are obtained?
The strain rate, I'm not sure if it's given on the slide. The velocity is some 40 meters per second of the parts, and the strain rate is in the order of 1 to 2,000 per second. So it's really at the beginning of high-speed forming, because it's 1,000 to 10,000 per second. And so due to that we have this positive effect on pure aluminium of increasing the strain.
So I think this is a factor for the improvement of the formability of the alloy.
Yeah. We think that's the reason for it.
Okay, other questions please? Comments? On microphone. Herman, take that.
Just a question about this process. I mean, if I see that laser shock forming, are there also works in literature on electromagnetic microforming?
I'm not aware about that, but maybe one has to look for.
Okay, because this would be an interesting complementary work to what you are doing here, because there the strain rates are 10 to the power 4, a little bit higher, but still very interesting in that direction.
Yeah.
Okay, good. Thank you.
Could be a good idea.
Yeah, thank you.
Okay, we can take one more question.
Now, I realize that your business is laser, so you're like the Chinese guy who has a hammer, all the problems looks like nails. So you want to do everything with laser. But I'm wondering, what is the practical application? And if I were in industry, would I use this technique or would I do other techniques to make similar parts? The last part you showed for Philips, for example, I'm sure they are not doing it with laser, they are doing by mechanical forming.
Sure, they are doing this at the moment with mechanical forming, and we also do classical mechanical forming in our collaborative research center. And what we are developing for them is the basic knowledge, for example, about the size effects and the ways how to care for these size effects and how to master it to get a controlled introduction of microforming industry, because nowadays it's many trial and error, and it starts with the problems that there is not a good simulation of these microforming processes, because at the moment we don't know what we have to care for in the simulation, and though we even can't look for the right material properties, for example.
Yeah, but does the application of laser processing look like a cost-effective way of doing it? I mean, I realize that it's important, the data that you have to generate for simulation, of course, I agree with you 100%, but does laser, this kind of operation, does that look cost-effective compared to classical metal forming type of thing?
If you use this for joining, for example, for joining purposes, you can imagine that you have mounted or positioned already the parts, and then you don't need a mechanical punch and use this laser, and the speed cannot be beaten by any mechanical process, because 4 microseconds per process, so this means, let's say, 10 microseconds for one part, so this means 100 parts per second, this means 60,000 joints per minute, and do this mechanically.
Those numbers are a little bit misleading, because you got to move the part, you got to take it in and out.
Yeah, so then the limiting thing is moving the part and not moving the punch. Sure. Because if you move the punch, you have to accelerate all the masses and so on, and you don't need this with this process. And you even can scan the laser very quickly by scanner systems, and on the fly you could join at different places, and this could be an application.
Okay, thank you very much once again. Oh, Professor Roll, did you have a question? Yeah.
When you simulate this process, can you use the classical equations, or what is your heat surface, or what is or can you simulate this process?
For microforming generally, or for one of the special?
For microforming generally.
So generally we try to use the same principle of FEM simulation, but it has to be combined, so this is the way we are now working on. We combine it as in a way of multi-scale simulation, for getting first with a Monte Carlo simulation the material behavior within a small but big enough volume to get the effect of the scatter, and then scale it up to the whole part. So this could be the way to get the information about the scatter.
Okay, well, we would like to thank once again to Boris Wollersen for his excellent presentation. Now our next presenter is Professor Yang from Korea, and he is from Korean Advanced Institute of Science and Technology, a very well institute known as KAIST. And the subject of his presentation is New Insights into Incremental Forming as Flexible Forming Technology. Thank you.